Hello, students. One more for this week, so welcome back. We are talking about transformations in the plane. So this tends to be one that a lot of students come in knowing the general concept of, and then we just kind of dive in a little bit deeper. So I am going to make that assumption, but if you really are struggling with this, let me know, because there's a lot of stuff that we can go over to talk about the basics. So let's do the basics kind of quick, but a transformation. So when we talk about a transformation, is a function that takes points in the plane as inputs and gives others as outputs. We talk about a pre-image and mapping onto the image. So the biggest thing there I want you to make sure you understand is that the pre-image is the first figure and the image is the second figure. And then we talk specifically about rigid motions, which are a type of transformation, which are also referred to as a congruence transformation. We will use that term, and we will use the term isometry. So this is something I would recognize and know. Again, you don't have to know the definition of it, but you need to understand it and be able to identify one. Okay, and it's a transformation that preserves distance and angle measure. So the big transformations, the three main type of transformations we talk about, are the reflection, the translation, and then the rotation. So reflection, translation, and rotation. And most of that is something that you should have heard about. Now, if I take these other terms and put it in there, a transformation is the overall concept of what these three things are. Okay. The pre-image and the image, for each one of these, you're going to have a pre-image and an image, the start and the end. Okay. And all three of these are actually rigid motions, which are also called congruence transformations, which are also called isometries. Okay. So all three of these are that way. Now we're going to talk about these three pretty extensively. So I want you to understand, then you're thinking to yourself, well, what is not a rigid motion? So the example there would be a dilation. Okay, so if you think about a dilation, that's the one that you guys know. There's other ones, but a dilation would be an example of a non-rigid motion. Okay, so think about like your eyes dilating. They get bigger or smaller. That idea, that's a non-rigid motion, because it's, in that case, it's not keeping it congruent. It's not preserving distance. It's making it bigger or smaller. It's not preserving angle measure. Okay, so these are my three main types here. We are going to also use what is called prime notation. So to indicate transformation. So if you see A is going to be in the pre-image, which is the original figure. And then it's called A prime. I know it's A apostrophe, and you're like, what's going on here? This is math talk. So this for us is A prime is the image after one transformation. So if we start with A and we want to move it to the side, then that's going to be A prime, because we've moved A a certain amount. Okay, so reflection is your simple flip. So you see your reflection here. We take one figure and we flip it over a line and we get a new figure. You're starting to see that prime notation there, A to A prime, B to B prime, C to C prime. Okay, so that is a reflection or a flip. Here we have a translation or a slide. So we took our blue figure and we just slid it down and made it into that green figure that's there. And then the last one, we have a rotation. We take our blue figure, we rotate it about this center point. So imagine yourself, rotating something. Hold your hand out, rotate it, and that's going to be a rotation there. You can even take it and then you can rotate it. And I haven't changed the size of my hand. All I did was I moved it around an axis, and I did that around my elbow, for instance. So those are your main types of transformations. Okay, so identifying them in the real world. A landscape, so like this right here, you see the landscape up top, and then you see the mirror image of it down below. This is just an example of a reflection. So understanding that idea there. In the game of checkers, when you move a counter, a marker, a certain amount, and you move it from there, that's going to be our translation. Okay, it's moving, it's sliding that chip from one place to another. That's going to be a translation that's there. Identifying transformations in the coordinate plane. So being able to look at something and say, is this a reflection, a translation, or a rotation? So for this one, this can actually be a little bit tricky. Some of you might be, okay, a reflection. Well, here's what I would test you if you're going to say a reflection is, where do you draw the line to where it reflects over it and goes to the other? And what you're going to find in this one, and this is a tricky one to start off with to know that, but it doesn't work really well. Okay, it's not like I can go from one to the other for each one of these points in the same direction. So this is not a reflection in that case. So that line doesn't work. Rotation, you could argue a rotation here. Then you're going to ask the question of, where is the center of that rotation? And in this case, that's where that one's going to go a little bit awry, and you're like, I don't know. And that's a little bit tricky, but that rotation center is going to be somewhere in here, even at a decimal of an amount. You argue it? Yes, the easiest one here is a translation, because each vertex goes the same distance to get to its next one and in the same direction. And that's why you're seeing these things marked as congruent, because each one of those vertices goes the same distance and goes in the same direction. And that's exactly what a translation is. Okay. So that's a translation. Versus B down here, we've got these two. So we've got the crescent moon here and then the other crescent moon that's there. For this one is going to be a reflection. So we're not going to have a translation. That's pretty clear. Could we have a rotation? Yes. And this one really wouldn't be that bad. It'd be about this point right here. Okay. But the easiest one for this one is that each point and its image are the same distance from the y-axis. So this is a reflection in this case. So is there a line of reflection to go between these? Yes, there is a line of reflection that's easy to find. Everything reflects on the other side with it, so that's a reflection. And then the last one, pretty clearly here, not a translation. You can't take this point and move it. Like if I move this point here, right, that goes there, and then this point goes here. One, they're not the same distance, and one, they're not in the same direction. So neither one of those things works for that one. And that's why we take that off the board. So not a translation. Reflection, you would have to ask yourself, where's the line? Well, it doesn't match up on the other side, so we can't have a reflection there. And then there's really only one other answer. And this one's a rotation. They show you the center right here, and they show you that if you connect to this point and connect to its other one, it's the same distance away. And we went that degree measure, which actually looks like a 90-degree rotation here. You can do that with every one of those points to figure out that it does rotate. So what you're seeing here is each vertex and its image, so pre-image and image, are the same distance from the origin. The angles formed by each pair of corresponding points in the origin are congruent. So this is a rotation, and that gives you an idea of what a rotation is like. Okay, so to check, you look at this figure. Hopefully you figure out pretty quickly that that is also a rotation. Okay. So representing reflections. In a reflection, each point of the pre-image and its corresponding point on the image are the same distance from the line of reflection. So when we think reflections, a lot of times I'm just going to be asking you, where's the line? Okay, a reflection can be described as a function in which the pre-image is reflected in the line of reflection. The points of the pre-image are the input, and the corresponding points of the image are the output here. So we're going to look at for that line of reflection here. Specifically and simplified, we're going to look at reflections in the x and the y-axis. Now it does get more complicated later on, not quite yet. Okay, so we're going to reflect in the x-axis. So if we reflect in the x-axis, we're going to multiply the y-coordinate by -1. Now, I don't like to memorize these. I like to think about what is happening. I like to draw myself a picture as we go. You're also going to have the symbols. So this is called coordinate notation here that you're going to see. And what this is saying is if you take the pre-image x, y, and every single time the pre-image is just represented by an x value and a y value, and you change it, your new values are going to be that same x value, and you're going to negate the y value. Okay, that's how that works. What I like to do is just say, okay, give myself a picture, draw myself a point. So they've got a point of 4, 1. So I'd go over here to A, and I would say, okay, if I reflect this in the x-axis, I'm going to go on the other side of the x-axis to find my A prime. And where's that going to be? It's going to be at a positive 4, -1, and I find that point. Okay, you can see that here. Now, the one thing that I have some students struggle with is where does the reflection point go? So if this is my point, how do I know that B prime is down here and not maybe over here? You do need to realize that this point is going to go perpendicular to the line of reflection. So this x-axis here is my line of reflection. I'm going to go perpendicular to that, and I'm going to go perpendicular on the other side the same distance. Okay, so that's how you do a reflection, and that's why this ends up at 7, -3. If you do this in the y-axis, almost the same thing, but technically, again, if you want to memorize, you multiply the x-coordinate by -1, so that's what you're seeing in this coordinate notation here, and then you move them. So again, my A is at 2, 3, then my A prime becomes -2, 3. Okay, I take it over the y-axis, I go perpendicular to the y-axis, perpendicular on the other side, the same amount. Okay, and that's how you find your reflections that are there. So you have your reflections in the x and the y-axis. You can do your reflections and perform them. So graphing the triangle, and predict your results. So you can take this triangle right here. Sorry, I should read the beginning of it. We have all of those coordinates. Determine the coordinates of the vertices of the image after reflection in the x-axis. Okay, so I'm going to take my x-axis right here, and I'm going to reflect each one of them. This is actually a really good example to start with. So A is up here. If I'm reflecting in the x-axis, I'm going to go perpendicular to it. So that's going to take me down 2 units. So I went down 2 units, and that's perpendicular. I went vertical because x is horizontal, and I'm going to go down another 2 units, and that's going to get me to my A prime point. And so that's where A prime is. Okay. Now, a lot of students will get stuck on this next one because you're like, okay, well, what do I do with B? Because B is already down here. Well, you go to your x-axis. So I go to my x-axis. I go up 2 units. And so I go up on the other side 2 units, and that gets me to my B prime point. And yes, A prime and B prime can be on opposite sides. So if I do my last one, my C point is going to be up 1, 2, 3, 4, 5 units. And so I'm going to go up 5 units on the other side, and I'm going to get to my C prime point. Sorry, I ran off the page there. C prime point, and then I can connect the dots to find my figure that is reflected. And that's going to be my reflected image right there, is my A prime, B prime, C prime. Okay, so I reflected everything. Now, what they go through within here is all of the coordinates by multiplying the y coordinate of each vertex by -1 and finding those. I can easily find those on my graph as well. Okay, and you can check to see that that matches. So part B is reflected in the y-axis and determine the coordinates. I'm going to do the same thing, but I'm going across the y-axis. So the y-axis is vertical, so I'm going to go from my point and I'm going to go horizontal. So I go over 1, 2, 3 units, and I'm going to go 3 units on the other side to find my A prime. And again, A prime tells me that it's my image of A. Do the same thing with B. So B is 2 units this way, 2 units on the other side. That's going to give me B prime. And do the same thing with C. I'm 4 units over. I'm going to get to C prime. I'm going to mark all of those, label all of those pieces, and I'm going to connect the dots. And I have my image there. That's my reflection. Okay. Again, they have showed you how you can multiply the x coordinate by -1. To me, it's another thing to remember. I'm able to visualize this a lot better, and I think that's a better understanding of it. Okay. So then they give you a check, triangle JKL. And again, anytime you get to these checks, my suggestion, pause the video real quick. Do it yourself, then listen to me. So triangle JKL has coordinates given here. Determine the coordinates of the vertices of the image after reflection in the x-axis. So here's what I do is I take one of those points. So 2, -8, approximately down here. Okay. And I say I'm going across the x-axis, which is right here. So I'm going to have a point that comes way up here. And what I know is that that's going to be a positive number, so still 2 over, and it's going to be a positive number up. So instead of 8 down, I'm going 8 up. And so that's going to take me to 2, 8. Now, just based on that, I know my answer because there's only one answer that has that coordinate. If I wasn't sure if there were 2 answers that had that, which is possible, I check my next coordinate because there's no chance that all 3 of them are the same in that case. Okay, but I got to a positive 2, positive 8 there. So suppose the coordinates of A are 5, -2, and the coordinates of A prime are 5, 2. Describe the transformations. So what I would look at in this case, just a different way of asking the question, right? So I look at A is at 5, -2. So I have my A, and A prime is at 5, 2. Then I look at it and say, okay, where's the middle of those two? So the middle of those two is in here, and that is over the x-axis, and I can explain that that is a reflection over the x-axis. Now, this one does not specify, so technically, could you say that this is a translation or a rotation? Absolutely, yes, okay? I would probably ask this and specifically say, what is the line of reflection here? Okay, but just to open that up, that's kind of a different way to ask it. Okay, so translations. A translation is a function in which all of the points of a figure move the same distance and in the same direction. Okay, a preimage is translated along a translation vector. So here's a new word for you, a vector. Okay, all this is saying a vector describes a magnitude, which is like a distance or an amount. Think about a magnitude of an earthquake. It tells you how big or how strong the earthquake was. So this is going to be the amount of the distance that you go, and the direction. So the vector is going to tell you a magnitude and a direction of the slide. And the magnitude is the length of the vector from its initial point to its terminal point. So when you think about a vector, it's going to look like a ray. It's going to look something like this. But what this is showing me is that whatever this figure is going to move right and up. Okay. And it's going to move just that far. Okay, so there's my magnitude and my direction, right and up, that it's giving us. To describe a translation in the coordinate plane, it is helpful to write a vector in what's called component form. So here's another thing. There's just a lot going on in this section here. But component form is written as, and please, please, please notice that this component form here has, I call them arrow brackets. So it's going to be an arrow bracket, and however far over to the right, let's say that this went 3 units to the right, that would be a positive 3 because right is positive. And since it went up a certain amount, then it would be, let's say that was 5 units, it'd be a positive 5 and an arrow bracket. That would be the component form of that vector. And what that tells us is how far and in what direction that vector is going. Okay, so that's the idea of a vector. If you're not understanding vectors, you absolutely can look up some videos on vectors or ask more questions about them too. Okay, so key concepts of translations. You translate usually based on a vector or an amount. Okay, so we're going to be giving you a vector that's going to tell you the translation. The coordinate notation for this is going to be XY. Every one of these would start with XY. So it starts with a pre-image point. And what you do is you just add your A component to the X and you add your B component to the Y, and that gives you your new coordinates. So for instance, in here, it shows you that example. Take the point P at -2, 3. So that's my X and my Y. Okay, here's my X and here's my Y. Translated along the vector of 7, 4. So all you do is you take your X of -2 and your A value, that is the 7, and add those together. So that's where you get the 5. And then you take your Y value, the 3, and your B value, the 4, add those together, and that's where you get the 7, and you get your new point. So you had taken your point -2, 3, you'd move it 7 to the right and 4 up, and you end up with your new point that is there. Okay, so that's the idea of that. We've been using this word preserved, or you've seen this word preserved. Okay, all that means is because it is a rigid motion, all lengths and angle measures are preserved in the translation. That means that they stay the same. So when if I take this triangle and I translate it over here and make this triangle, the length of this side and the length of this side stay the same. I didn't change that. As well as like the angle measure of this one and the angle measure of this one stayed the same. I don't change that. So we preserve those measurements as we move them within each one of these transformations. Okay, your translations, these are usually the ones that people like the most. Okay, we have a quadrilateral that's given to us. Find the coordinates of the vertices of an image after a translation along a vector of 7, 1. So you can draw yourself a picture. You can use the coordinates. I actually find these just fairly easy to work through and just say, okay, I'm just going to add 7 to -8. I'm going to add 1 to -2. So I'm just going to do +7 +1. And that would take me to a Q prime value that's at -1, -1. And I would have my Q prime. And I could do that to each one of those in order to get these different values here. Okay, and seeing where we would be at. So if I do that same idea to this check, again, we're at a check. So if you want to pause and come back, you can. But we have a quadrilateral given the vertices here, coordinates of the vertices of the image after translation along vector 5, -3. So all I do is I take this, I add 5, I subtract 3. So I'm going to get a point at 2, -2. And there's only one answer with an A prime there. So we're going to go with that one, and I don't have to worry about checking the rest of them. Okay, but that's all you're doing is you're just applying that coordinate to it. Rotations, we have reflections we've talked about, translations we've talked about, translations and vectors. A rotation is a function that moves every point of a pre-image through a specified angle, so a specific angle, and a direction about a fixed point. Okay, lots to go on here. So under rotation, each point in this image are at the same distance from the center of rotation. In this lesson, you can assume that the origin is the center of rotation. The specified angle is called the angle of rotation. So we are going to rotate clockwise and counterclockwise, okay? If you see clockwise, you will see CW, and you're welcome to use that. Counterclockwise, see CW. So if you see either one of those notations used, you can use those. No clockwise, no counterclockwise, so that you can talk about those. But we do assume that rotations are counterclockwise unless otherwise stated. Now, that seems really weird to a lot of people. I'm going to do a little bit of math talk that's in the future, kind of your algebra 2 trig. But when you get to that, when we look at a coordinate plane in terms of like polar coordinates and in terms of trig, this is 0 degrees, and then, and then this is 90 degrees and then 180. And so if you follow this, we actually go counterclockwise when we're doing math. And so that's where this counterclockwise idea kind of comes into play. But we do assume counterclockwise unless it's stated otherwise. So it says a 90-degree rotation, you go counterclockwise 90 degrees. Okay. So let's see what we have here. So your first one here, a 90-degree rotation counterclockwise. Okay. actually does have a rule that it follows if you want to memorize it, and you have some symbols that you can memorize as well as to what happens. Okay. Now, you also have the same thing come up for 180 degrees, and you have the same thing come up for 270 degrees. Okay. Where you have some rules that you can follow with each of those. What I like to do, one second here. I think, did I give myself? Nope, I didn't. Okay. I'm just going to use this one up here. Okay. So what I like to do with these, actually, I'm going to just use a space in here. So let's say that I'm going to try to take this point at, we'll use 2, 4. So I'm going to take that point at 2, 4, and I am going to try to rotate it. Okay, so here is, let's see if I can do this. I'm not going to let me do that. Hold on. Can I? Sometimes you have to be smarter than this stuff, but sometimes I'm not. So I got to think about if I can pick up all of that I just put down. Did I get it? Oh, I think I did. And then I can rotate it. I don't know that it's going to let me do that. Nope, that just made it smaller and bigger, which does not help. Okay, I guess I don't get to do my fun. So you know what? I will do that part in class to show you guys how to rotate easier without having to do it. But essentially what I want you to think about right now, if you have this on your paper, let's say that I want to do a 90 degrees counterclockwise rotation about the origin. What I'm going to do is take my whole paper. So if you have this drawn on your paper, and I am going to rotate my paper 90 degrees counterclockwise. So that would be turning my paper this direction 90 degrees. And so really right now, this would be up. Okay, if you can follow that. And I would reread my point. So if this is up, this point is at -4, +2. And that would be my new coordinates. Now, if I come back to the 90 degrees counterclockwise idea here, that's what I would get out of this. So if I was at the coordinates of 2, 4, like that says, I would write these as the y value negative, so -4, 2, and I would get to that. And that's exactly what I kind of showed here. Again, I'm going to do this in class since I can't rotate on the board, but that's a good thing to know here. Other idea, 2 successive 90-degree rotations counterclockwise about the origin rotates in the exact same way as it would if you did one 180-degree rotation. Okay, so do understand that if you put 2 rotations together, as long as they're about the same point, which they are in this case, then you do get the exact same rotation in the end. Okay. We're given a 180-degree rotation here. What are the coordinates of the vertices of its image after a rotation of 180 degrees about the origin? So you would take your F, you would go 180 degrees. Again, I would just flip my paper completely over. I know there's some way to do this, and it's driving me nuts, you guys, but I don't think I can do it right now. So I'm just going to have to leave it. So I would rotate my entire paper right now, and then I would look at it, and that point would read as -2, -1. And so then I'd rotate back, and I would plot -2, -1, and get my F prime. And I would do that with each one of my points to figure out those new coordinates. Again, they show you the rules here, so I will have to go over that in class and kind of going through that idea. So I'm going to skip this one and use that as my example that I can go over in class and leave the video where it is for now.